Okay, looks like we're recording. Okay, good. So, welcome to Math219. First, just a little bit of arithmetic fun. I imagine most of y'all have probably already seen this, but isn't that wild, right? The 20 plus 25 quantity squared thing is aesthetically remarkable, I think. But for whatever it's worth, notice this one down here, the sum of the first 9 perfect cubes. If you think about it, that's not going to happen again for another 1,000 years. That's kind of wild, right? So anyway, fun with numbers. Okay, so y'all have already received an email from me where I went through all of these notes. I always feel like it's necessary at the start of the course to go through and talk about some logistical stuff just so you know kind of how it's going to work, right? But then also philosophical stuff. What are we doing here, right? What is our goal in this course and stuff like that? Because very often students have taken previous math courses that don't have that same philosophy. Right? So make sure to watch that recording. I'm not going to go through it all again, but just because of the importance, I want to emphasize this course is about ideas in reasoning. Right? Cannot emphasize that enough. If you take a memorize and regurgitate, or I'm going to rehearse all the algorithms kind of approach to the course, it's not what we're doing in this course. That's not the goal of this course, and so therefore it's probably not going to go super well. Now, of course, you do have to know the formulas, and you do have to be proficient with the algorithms, but that is step one. That is not the goal. Okay, so I'm not going to get up on that soapbox again, but today, probably will again. But the other thing I want to make sure to hit again is that, again, don't expect that, you come to class, you listen, you leave, and that's how you learn in this course. Again, that's not realistic, right? There's too much material. It's too challenging. It's not realistic at all, right? So make sure that you are prepared. And again, I went on at length about this in the recording, of course. Make sure that you have an explicit plan to do a tremendous amount of learning outside of class. There's various different resources that y'all have at your disposal, various different ways that, different people learn in different ways, different people prefer to study in different ways, whatever, right? But make sure that you do have an extensive and thoughtful plan about how you're going to learn outside of class, and keep in mind all the resources that you have to choose from. Okay, all right. So then on to a little bit of math. Now, the first couple pages of my notes here are just introductory, mathematically, what are we doing here? Why are we taking a course in multivariable calculus? And I do know that for many of you, the answer is because it's required, right? Okay, sure, right? So natural next question, why did your majors require it, right? And there's great answers to that question. That's what I'm going to attempt to address here. I'm going to take as a starting point that you've already presumably bought in to what I think is a very well-established claim. Single variable calculus is extremely important, right? Single variable calculus, among other things, studies how things change. That's what derivatives are, right? And how to add stuff up. Loosely speaking, right? That's what integrals are. So there are lots and lots of things of interest that change. So bam, right? So that I think that's pithy and I think highly persuasive argument as to why we need to understand calculus. Stuff changes. Derivatives are how you keep track of that, right? Pretty easy pitch. Accumulating quantities. This is a term that I use for things where the whole is the sum of the parts. Right? So many, not all, but many things are accumulating quantities, and that's what integrals do. Right? So the world full of accumulating quantities. How do you study that? Single variable calculus, or so we've done so far. Okay. So the complaint I'll make about this is that the world is, of course, three-dimensional, not one-dimensional. I'm sure you noticed. Right? So that in mind, here's a couple of I'm going to say three-dimensional versions of the problems that we just talked about. So how do we keep track of how stuff changes? Well, if temperature were a function of just x, that'd be a single variable calculus problem. You want to know how the temperature changes with respect to x, you take the derivative of that function of x. And it's very straightforward. But if temperature depends on three coordinates, such as in this picture, by the way, such as in this room, right? It's warmer near the ceiling. It's probably warmer maybe over in some corner where there's not good, circulation or something like that, right? Probably colder underneath the desk here where it's completely in the shade and down low. So temperature in this room is a function of three variables, right? So x, y, z. And in such a scenario, if you were to write down a formula for the temperature in this room, it would involve three variables. Well, for one thing, we don't know how to take a derivative yet of a function of three variables. So there's that little problem. But then let's entertain the reasonable physical scenario. Suppose I'm at that point and I take off and start moving with some velocity, like, that way. Well, it's not in the x direction, it's not in the y direction, it's not in the z direction. You can't say, well, I'm just going to, take the derivative. I'm going to pretend that it's a function of a single variable and just kind of take a single variable calculus approach. Won't work. You're not moving in the direction of a single variable. How do you address this problem? Right? Single variable calculus is not good at this question. So we need a more powerful tool. We need a broader tool, and multivariable calculus is ultimately going to be our answer to that question. Let's see, related, sort of simple, low-hanging fruit, easy example. Suppose you have a lump, and suppose that the density is a function of three variables again. Now, y'all have seen density problems in your single variable calculus classes. A classic example is you've got a tank that has some sort of oily, sludgy kind of stuff in it, and for whatever reason, the denser sludge is at the bottom and the more lightweight sludge is at the top, right? And then they ask you to compute the mass of that whole thing, and Calc 1 will do that. However, in that scenario, density only depends on height. Density is a function of a single variable, right? So it's ultimately a single variable problem. Not so in this example. In this example, my density depends on three different variables. There might be a dense spot in here where maybe there's a little bit more like iron ore or something, just in this one little spot there. And then maybe it's very lightweight over here. There's some sort of igneous rock in this section. And then over here, maybe it's denser again. Right? Some weird random function of several variables. How would I compute the total mass? Calc 1 falls on its face. Crash and burn. Doesn't work. We need another method. I mean, this is still, it's kind of like a single variable integral question in the sense that I want the whole to be the sum of the parts. I kind of want to add up a bunch of little pieces, but we don't know how to do that when there's three variables to deal with. So multivariable calculus is going to be the tool that allows us to answer that question as well. So these are just easy examples, sort of obvious examples of when the world is three-dimensional, how do things change? How does calculus change? So now, to make the case that we need much more than just this, I'm going to show you some sort of field-specific kinds of examples. Now, full disclosure, I don't know much about economics, right? But I have studied it a little bit, and I'm aware that there are these things called economic models, and very often economic models are equations. So what I did here is I wrote down an equation. This is not a real economic model that I'm aware of. If it were, that would be the craziest coincidence ever. I just wrote down some random stuff. The point is, this is what economic models look like. Very often it's an equation involving several variables where, in particular, the variable that you want to study, maybe P, whatever that is, price probably. If you want to understand how that thing changes, very often in economics, it is the case that you can't solve for it. Right? Look how P shows up in this equation. You can't solve for P analytically. Or I can't. I don't think it could be done. So, do we lose? Right? Can't do anything with this. If you can't solve for P, you can't take its derivative. Is a common mistake to think. Right? Turns out multivariable calculus will help us with this as well. We're going to be able to understand the derivative of something we can't even solve for using multivariable calculus methods. Really big deal in econ. By the way, if there's any econ majors in the room, this is an example of the kind of thing that motivates econ to require students to have a course in multivariable calculus. You can't do economics reasonably without it. Okay, let me take a quick pause. I have a tendency to kind of go on and on and on and not leave room for people to squeeze a word in edgewise. So I'm going to pause periodically as it occurs to me. This is not intended to be in lieu of you having the right to raise your hand, of course, right? Raise your hand and ask a question anytime. But I am going to try to force myself every so often to allow a little dead air, see if anybody has a question. Everybody good? All right. Okay, here's another thing I like about this example. This dispels what I would call a very common misunderstanding / mistake. A lot of people like to make the case that, look, we live in a three-dimensional world. I mean, I said it myself about 3 minutes ago. Right? We live in a three-dimensional world, and a lot of people conclude from that we only need up to 3 dimensions. Wow, that's just nonsense. It's absolutely not true. That assumes that the variables that you're going to be using will always represent physical location in our three-dimensional world. And it's just not true. Right? And this is an easy, no big deal, unsophisticated example. Right here, I'm just talking about economic variables, price and quantity and interest rates and other, real economics, real world kind of stuff. And yet, I end up with an equation that involves 6 variables. We are doing math here in 6 dimensions. Does that mean that we've proved something about the physical universe? Is this a science fiction film that we weren't aware of? No, not at all. Right? This math doesn't have anything to do with spatial dimensions. So anyway, we need to understand more than 3-dimensional math just because, well, we're going to encounter some more than 3-dimensional problems with non-coordinate, non-physical, non-dimensional kind of variables. By the way, ditto in engineering. You might have an equation not describing an economic model, but describing relationships between engine efficiency and combustion temperature and richness proportion and various other factors that go into describing how an engine works. Well, again, so you would have an equation with a bunch of variables, and you're doing 8-dimensional math. So very practical reasons. Okay, here's some more physics and engineering stuff. You may have seen some of these equations before. If not, you'll see them soon. Taking a physics class in electricity and magnetism. Everything that's written on the board is heavily in the language of multivariable calculus, as it turns out. Right. So the laws, Maxwell's equations that describe how electricity and magnetism work, some of the most important physics that you will use in engineering. Not only uses multivariable calculus, it kind of is multivariable calculus. Right? That's how you say those things. So there's a lot we need to study about this, and in particular, there's questions of what does this stuff mean, right? So what does that symbol mean? What does that symbol mean? What does that symbol mean? We're going to answer a bunch of those questions. Yeah, sure. But we're going to be interested, of course, in much more than that. So we are also going to be interested in this statement, right? How should I think about that statement? What does that expression on the left, like why does that expression on the left have anything to do with that expression on the right? It's not just, it was, written down on stone tablets, and so therefore we believe it, right? There's reasons why that's true. And we're here to understand those reasons, right? And then furthermore, I claim, understanding those reasons, understanding why these equations are true, will help us to get a better fundamental understanding of the quantities involved. So, for example, you're going to need to understand electric fields. Not just that you need to be able to manipulate equations, you need to have a good intuition for how electric fields behave. And the way you're going to get that, right, is going to be a consequence of understanding this calculus and understanding the relationships between these mathematical objects, and then reasoning from that and being able to draw some cool conclusions. Okay. All right. Okay, let's see, moving along. This one is a little bit of a reach, but I think it's just a really cool example. Chemistry. There may be a chemistry major in the audience, perhaps. Well, if you're a chemistry major, you're going to need to understand molecular bonds, because that's pretty fundamental in chemistry, right? That's how things combine. That's how chemistry works fundamentally. How do molecular bonds happen? Well, they come from understanding the behavior of electrons. What controls the behavior of electrons? Schrodinger's equation, quantum mechanics. Right? So ultimately, deep down, if you're doing chemistry, you're doing kind of what you might call applied quantum mechanics. Okay, what is quantum mechanics and how do we understand it? Well, this right here, one of the major players, is an object of multivariable calculus that we're going to be learning about in this course. And arguably take a couple of different points of view, maybe some of these other things as well. Okay. All right. How we doing? Pausing for questions. Okay. So I hope you buy my pitch. This is the pithy summary that says it all, in my opinion. This is why your major requires you to take multivariable calculus. It's the calculus of the real world. It's how stuff works. And single variable calculus, very important, very cool, yeah. Kind of a starter example in calculus, right? That's a good first step, right? But to really make calculus work and apply in real settings, you need multivariable calculus. Okay, so there we go. Let's dive in. One of the things I talked about in the recording that I hope you all have had a chance to watch by now, if not, sometime as soon as possible, of course. One of the things I talked about is, again, I'm not going to be able to cover everything in class. There's a bunch of stuff that I think is important that either is or isn't in the book, not really the point, but that I have in my lecture notes because in past semesters I've spent time on it, and I do think the lecture notes are going to be useful for you. I don't want to remove it from the lecture notes, but I also have kind of made the tough, frustrating decision of, I don't think this quite makes the cut of being worthy of the precious, precious little class time that we have. So a lot of this stuff I have annotated like so. So you're going to find this in various places throughout the lecture notes. This is good stuff. I want you to read it. This is necessary. You are responsible for it. But we just don't have the time. We've got much bigger fish to fry, and we can't spend time on this stuff. So be on the lookout for this. I will make references to it as we go along, but you might want to make notes to yourself to make sure to go back and read the stuff that I kind of skip over. Okay, so this I do want to talk about. This is a very underappreciated, in my opinion, underappreciated fact about linear algebra, about how to multiply a matrix times a vector. A lot of people are kind of bored at the concept of how to multiply a matrix times a vector because after all, you learned it in high school, and there's a little arithmetic method, and you go across the rows and down the column vector, and that, this kind of multiply and add, and then you just kind of go down the rows. And that's fine, that does work if your goal is to do arithmetic. Very often that's not our goal, right? That's kind of a high school point of view on that sort of thing. Very often our goal in writing down matrix vector products and manipulating related algebra is to understand something deeper, see what's going on, try to understand how things, important mathematical objects are related to each other, stuff like that. From that point of view, that high school dot product formula on how to do matrix multiplication, it does have its uses. I think it's probably third most useful point of view on matrix vector products. If I had to rank them, I'd call that number 3. This is what I'm going to call number 1. I think this is the best way. This is the way that I've gotten the most value. I will say it's neck and neck. Number 1, number 2. There's another angle that we're not going to use very much in this course. But anyway, the one I want to focus on in this course is that matrix vector products are linear combinations, which isn't the high school take at all. Right? Linear combinations is an idea that doesn't even usually come up in high school classes. It didn't come up in mine anyway. So linear combinations of what? Well, linear combinations of these column vectors. And already we see that we have here not just a formula for executing arithmetic. Boring, right? What we have here is a relationship between mathematical objects. This is a tool for manipulating and eventually, hopefully, understanding important ideas. Right? A matrix and its columns relate to multiplication by linear combinations. Those are ideas. Does everybody see what I'm talking about there? Right. And how you use this to prove cool stuff comes up in various different ways. We're going to use it in several places in this course. And you'll use it in several places in other courses, other math courses, probably other engineering, physics, whatever courses. Anyway, I think this is a really nice point of view. Now, linear combination with what coefficients? Well, we're going to use the vector, specifically the coordinates of the vector, right? This vector that I'm multiplying by, as the coefficients, and you see that right here. Right? The coefficients in that linear combination are the coordinates of the vector you're multiplying by. So really neat, the pieces kind of all fit together. Everything just kind of dovetails there, and really nice fact, very powerful point of view. So I wanted to make sure everybody has seen this. I want to encourage you to take this as your cornerstone point of view on what it means to multiply a matrix times a vector. This isn't a linear algebra class, so there are, like I say, other points of view as well. But make sure you're good with this one. Okay. All right, moving along. Now again, here's another for students to read. So I'm going to be very brief about this. Sometimes in this, students to read sections, I will say a couple words just to kind of get you going in the right direction. This definition of the word linear, what does it mean for a function to be linear? If you think about it, the field called linear algebra, right, rests on this definition. So it's very, very, very important to understand what this is. This describes the kinds of functions that are studied in this field of linear algebra, which by the way, in the same way that multivariable calculus is the natural sort of real-world extension of single variable calculus, in a similar way, linear algebra is kind of what I would call algebra 1 for multiple variables. Right? It's extremely fundamental. Right? It's a super big deal. There's, linear transformations are all over the place in the real world. So very important to be good at linear algebra. Now, real quick comment about, y'all took actual linear algebra courses here. We're not going to use all of what you learned in your linear algebra courses. We're just going to use kind of what I'm going to call the fundamentals. And y'all, again, heard me talk about this on the recording a couple days ago, whenever that was. And so anyway, you want to make sure to be good with those fundamentals. What is a matrix? What's the relationship between a matrix and a linear transformation? We're going to talk about that in a couple of minutes. Basic properties, what does linearity mean? This kind of thing. Make sure you're really good with. Okay. These are 3 different examples of linear transformations. I'm going to leave the details for y'all to think through, to prove these statements that these functions are linear. That's something to make sure that you can do. So you want to think about how would you go about writing that down. Of course, all you're going to do is invoke this definition and just confirm that these functions satisfy this definition. But again, good exercise. Make sure you can do that. Another little digression. I'm going to do this a lot. I'm going to say, hey, make sure you can do that. I'm happy to help, right? If you try to do it and find that you can't do it, I got to make sure I can do it, but I can't do it, come to my office hours. Right? I'm very happy to help. No problem. You, of course, have many other resources. Don't forget about the help room. Right? The help room is going to be open for several hours. I've forgotten exactly the schedule, but it's going to be open for several hours a week. No appointment necessary. Show up, ask questions. Right? So there's also that resource. And again, several others. Okay. So be prepared for me to point and say, make sure you can do that. If you get stuck, come to me for help. Okay, so what I want to talk about, though, is the kind of the sloppiness of how people talk about this kind of stuff. A lot of people will look at this statement and, in kind of math slang language, very reasonably, will say dot products are linear. Now, technically, dot products are not linear. Dot products are a binary operation. Right? 2 vectors go in. What would linearity even mean in a case like that? If you write down in any meaningful sense what it would mean for dot product to be linear, they're not. So to be clear, when we say that P is linear, what we're really saying is, look, I want to talk about the dot product, sure. But in particular, I want to think of the left vector as being fixed. I want to think about dot product with that left vector to be what a certain function does. This function I'm calling P. Notice that P, because A is fixed, A is part of what the function is, P acts on a single vector. Right? And as a function of that single vector x, that function P is linear. So that's what people mean. Now you can see why they like to streamline that with a little math slang and say dot product is linear, right? Because it's a lot less syllables, right? A lot easier than saying it precisely. But you need to be prepared for people to speak with accepted normal math slang and to interpret accordingly. So in that sense, dot product is linear, cross product is linear, and determinant, again, appropriately viewed as something that you do to a single vector x. In this case, that single bottom row vector, and how I have it written down here. This function, which again, closely related to determinant, right? But thought of as applying just to a single vector, everything else in the matrix being fixed as a constant. Determinant applying to that single bottom row vector is linear. Okay, so stuff to work out, and again, I think this is a really nice exercise. You want to think about, how would you go about proving something like this? Make sure you can do that. Again, come ask me if you have questions. And then let me also point out, by the way, another common bit of language around this property that I just described is to say that determinant is linear in the bottom row. After all, here, the way I have it set up, the bottom row is where the input vector goes. Right? So determinant is linear in the bottom row. With that same slang, determinant is also linear in every row. And it is linear in every column. And so this is called multilinearity of determinant. And the whole, there's a wonderful bit of math there, but that's more of a linear algebra thing. And again, that's not what we're here for. So, okay, a little cultural note. Okay, moving along. Now, another fundamental thing about linear algebra, this very, very strong relationship between linear transformations and matrices, specifically among Euclidean functions. Linear transformations are matrices. Now, again, I'm saying it a little bit sloppy for pithiness, right? For dramatic impact. But linear transformations are matrices. They're the same thing. Every linear transformation is a matrix. Every matrix is a linear transformation. Suitably interpreted. Okay, so really important fact, and again, I presume you've seen this. This is the biggest fact of linear algebra that we're going to use in this course. Is that linear transformations are matrices. Proving it in the up direction, namely showing that if you have a matrix and you make a function by way of that formula, showing that that is a linear transformation, that's a previous page, plug and chug, just make sure it satisfies the definition. That's pretty straightforward. Make sure you can do that. Again, come to me for help if you have questions. That part's pretty clear. What is tricky is proving it the other way. That if you have a Euclidean transformation showing that there exists a matrix that makes that work, how do I show that a matrix exists that has a certain property? And this is the tricky part. So I want to talk through this proof, and again, you might have seen it previously, but I think it's just important enough to be worth a little class time. Let me first talk about the big picture of the argument. This is very tall, so I'm going to try to squeeze it on there. The way we're going to show that there exists a matrix that has this property is I'm going to start with T of x, and then I'm going to compute and get AX. And you can see that right here in the algebra that I've done, right? I start with T of x, and I end by concluding that it is AX. Okay, so that's the calculation that we're going to be doing. The way I'm going to show that the matrix exists, by the way, this backwards capital E is a little math shorthand. That means there exists, or there is, something along those lines. Way I'm going to show the matrix exists is I'm going to just explicitly write down the formula for it. That's the formula. By the way, huge, important formula to make sure you remember. This formula for the magic matrix that turns every linear transformation into a matrix. That formula, super important. Make sure that you memorize that formula. Okay, so how does the argument go? Let's get into some details now. The argument goes by, keep in mind, I'm assuming that my function is linear. I'm allowed to assume linearity. And notice, here's where that linearity shows up. If I can get my thing to cooperate. There we go. This is where the linearity shows up, right there. You can see I have a linear combination going into the function, and I cite linearity to conclude that that gives me the same thing as the linear combination applied to the outputs from the function. So there's the linearity. My linearity. Having done that, it's all kind of all over but the shouting. I mean, my goal was to show that T of x can always be viewed as a matrix vector product. Okay, well, matrix vector product is a linear combination of columns, I've already shown that it's a linear combination of these things. So I have a linear combination of things that I want to be a linear combination of columns. So I'm going to make those things my columns. And I'm going to basically define myself to have won, right? So that's where this definition comes from. These things here, I need those to be my columns. So I define those to be my columns. And plugging that in down here gives us the win. Right? The things that I was taking a linear combination of, I make those my columns. Now I literally have a linear combination of columns, which is a matrix vector product. How are we doing? Everybody on board? Okay, super important. Let's take a quick moment to dwell on the magic matrix. This matrix, the matrix that we claim exists, the matrix that represents a linear transformation, that matrix is determined by this, namely, let your columns, now let me do this with a highlighter. Let your columns be the images, namely the outputs from your given function, the images of the standard basis vectors. And I'm going to zoom in on, this thing has to be over. Yeah, okay, there we go. The columns, let me do it again. The columns are the images of the standard basis vectors. That should be one of the phrases that you find your roommate finds you muttering in your sleep. Right? This is extremely fundamental, most important little pithy phrase in linear algebra, I would make the case. Columns are the images of the standard basis vectors. So, easy way to remember it, perhaps, also, but really important result. Whoops, I hit the wrong button. I wanted to hit that. There we go. Okay, all right. Now, a real quick, and again, this is a, for y'all to read thing, but let's talk about how to multiply a matrix times a matrix, right? So, with this pretty weird formula, by the way. Anybody ever kind of raise an eyebrow when you first saw the definition of matrix-matrix multiplication? Pretty weird. Where did they get that from? Who dreamed that up, and why are we all in line behind that person who dreamed up a weird formula? Right? I was very unhappy when I first saw the formula for matrix multiplication. Well, there's an excellent reason why we do it that way. It is not arbitrary. The formula we have for matrix multiplication is exactly what it has to be to make matrix multiplication correspond to compositions. If you have a couple of linear transformations, each one can be represented by a matrix. Yeah, sure, okay. If you want to compose those transformations, you are effectively multiplying those matrices. And now there's various different ways that you can make the case for how you ought to multiply matrices. I think this is a pretty good one. There are others and there are different contexts, but I think this is pretty pithy, right? Because composing functions, very natural. I don't need to make a pitch as to why we might want to compose functions, I hope. And so that's why we multiply matrices the way we do. Okay, this is, by the way, another good exercise to think through the details of. I wouldn't call this an easy exercise, by the way. It's not intractable. It's not inaccessible. You can totally do it, but it's going to require setting things up and being careful and thinking it through. So please do give that a try. And again, if you have trouble, come talk to me. Oh, speaking of office hours, right, is where you'll come talk to me. And I've set up my office hours to try to be as accessible as possible to as many students as possible. And here's the thing, y'all are already physically here, right? So when class is over in a bit, office hours will start in like 5 minutes. I've forgotten what I said. Let's see, class ends at, is it 11:20? Okay, and my office hours, I guess, start at 11:30. But the only reason I leave that little gap in there is sometimes I just need to run to the restroom or something. So anyway, I'll be in my office basically right after class. My office is just right down the hall on the left, room 123, right? So basically right after class, you have an opportunity to come talk to me. So anyway. Okay. Another for students to read. By the way, hopefully no surprise. The stuff that I think is the easiest, arguably. I mean, it's hard to define, arguably problematic, but some of the least typically challenging material for most students is the material at the beginning of the course, right? So hopefully no surprise here at the beginning of the course. There is a certain amount of stuff that we're going over more quickly, this stuff, so that we'll have more time to dwell on the much more challenging and sophisticated material we'll be doing at the end of the course. And it's gonna pay off big. So anyway, a couple things. Notational point, heads up about how I write vectors versus the book. This, I think, is a pretty good point that relies on, I'll say, the natural correspondence between points and vectors. So I hope this is something you all saw in your linear algebra class. There's a canonical, for any point, there is this corresponding thing called a position vector. Right? And this is a one-to-one correspondence. So this point here, for example, sure, it's a point, but you can think of it as its position vector. And let's see here, this point here, yeah, that's a point, but yeah, again, you can think of that as its position vector, and as such, notice the difference is that thing that the book likes to write like so. You know, the vector that goes from P1 to P2. So my own personal preference is to write this in a way that exposes useful stuff like algebra. And by the way, I'm sure this is something you've all noticed. Algebra, really useful, right? That's why we spend so much time doing algebra, is because that's how you solve problems in very, very, very many cases. So algebra is a good thing. I like notations that show the algebra so I can use the algebra. And anyway, that's a little kind of a personal soapbox thing. I just thought I'd mention. Lastly, very often we are going to need to refer to a generic vector, let's say in space. So x, y, z, pretty common thing to want to talk about. Sometimes x, y in 2 dimensions. But let's say x, y, z. It's nice to be able to give this a name. So that I can streamline the reference to this, again, generic vector in space. And as is a very common convention, I'm going to call this the R vector. Now, to be clear, in the past, in previous terms, I've called that the X vector. And there are some subsequent consequences to these choices that create trade-offs. Neither one of these choices is problem-free. So anyway, for reasons I don't want to go into now, I am sort of transitioning at this point into the more typical convention, which is to call it the R vector. Okay. All right, and let's see if I can... Whoops. There we go. Okay. All right. So we're done with section 1.6. We're done also now with section 1.1. Just as a procedural note, y'all remember from the video that I sent y'all that the class schedule shows where we are every day, goals, reality, and which sections we finished, defining what homeworks, what exercises are going to be included in which homework set. So when class is over, I'll be filling in at least 1.6 and 1.1 as stuff that we finished today because we have now already finished them. Okay, and we got a good time. Okay. Why don't I do another pause? Yes.
What does NB stand for?
There's what?
NB.
Oh, is that on the screen here somewhere?
Last page.
Last page. Oh, yeah, right. This is an abbreviation of a Latin phrase. I think it's something like nota bene or something like that. And it basically just means, hey, by the way, something to pay attention to. Yeah. It's pretty common, but I don't know the exact etymology on it. Yeah. Anybody else? Okay. So here's something you probably have not seen before. If you have, super. But I don't expect most students will have seen this. It's called a parametrization. This is a way of describing a curve. And most fundamentally, though, a parametrization is a function that gives position as a function of a parameter, thus the term parametrization. But for whatever it's worth, most of the time when we parameterize, we think of that being time. So position is a function of time. Position is a function of time. Let's see, what does that conjure physically? Position is a function of time. Well, motion. Right? That's what motion is that your position changes as time passes. Right? So a parameterization can be thought of as literally you're just describing the motion of a particle in either the plane or space or whatever dimension you're living in. So I like to think then about the result as being that the parameterization draws the curve. Right? If I were to take a pen and put it to paper and draw a curve, my pen tip would be moving. It has position as a function of time. A parameterization is arguably literally drawing out a curve. Okay, so the resultant curve is called a parametric curve, and the function that draws it is the parameterization. Okay, so let's see some examples. First example is a classic starter example. This right here is position as a function of time in 2 dimensions. Specifically, notice position x comma y. Remember, we write that going forward anyway with the vector r. So position, and it's a function of time, meaning its coordinates are both functions of time. Everybody good so far? So, what functions, you say? Well, x coordinate as a function of time is going to be cosine t, and y coordinate as a function of time is going to be sine t. This is the particular parameterization I want to talk about. So what is this parameter? What kind of motion is this? And it's obviously in the plane, by the way, 2 coordinates, 2 dimensions. What motion in the plane is this? And here's the clever observation. Notice that this equation is always satisfied. Specifically, if you take this formula for x and this formula for y, that equation always works. Pythagorean identity. Okay, now what does that tell us? Well, our parameterization is moving along in some way. It's describing some motion. It's drawing some curve. Oh, and by the way, the motion is always on the unit circle. What can you draw if your pen is not allowed to leave the unit circle? It's the unit circle, right? I mean, it's pretty immediate. So this is a nice example. Sometimes you get lucky. Sometimes the answer will just kind of drop into your lap. I mean, how did I know that these would satisfy that equation? I kind of remembered the Pythagorean identity, right? It's just lucky break. Oh my God, look at that. Just happens to work out sometimes. So it's something to keep a lookout for. How often that will happen, we'll see. But it's definitely something to be aware of. Okay, now this next example, that method will not work. Let's look at that. Parameterization. Again, notice position's a function of time. Got an x-coordinate formula. I've got a y-coordinate formula. By the way, don't forget, I won't necessarily always explicitly write, x equals the formula. Sometimes we'll just write just the formula. And you've got to remember, when you're talking about a parameterization, you've got to remember that is telling you the formula for x. Right? So this first coordinate is telling you x equals t minus 1. Okay. All right, so that's my formula for x. That's my formula for y. Here's the clever idea, and that is to notice that in the first equation, you can solve for t. Right? If x is t minus 1, then t is x plus 1. So solve for t in the first equation, and then plug that in to the second equation. Notice I'm just taking t equals x plus 1 and plugging that in. And then when you kind of multiply everything out, what you're left with, let's just get rid of that. What you're left with then is a relationship specifically between x and y. And again, we recognize this at this point. Right? That's the equation of a line, right? High school, middle school, maybe, the ancient, old news algebra. That's the equation of a line. So again, I conclude, I had this parameterization. I didn't know what it was, but I see now that every point on that parameterization is on this line. So this is parameterizing the line. At least part of the line, maybe not the whole line, but I think it's a pretty easy pitch. It's the whole line. Everybody good? Okay. All right. Now, here's another way you can understand this. Again, keeping in mind that the first formula is telling you your x. Second formula is telling you your y. You can just play the game of what algebraic process do I have to apply to the x formula to get the y formula. I just kind of start fiddling with it until that x expression turns into the y expression. And keeping track, after all, when you have an equation, whatever you do to one side, you have to do to the other side as well. Notice that the punchline is that we have a relationship between x and y, and conveniently, again, as it better be, same relationship between x and y. So this gives us the same conclusion by way of a different method, a different little process that we apply. Everybody good? All right, so now I have at this point shown you 3 different methods for how to identify and understand a parameterization. We've got the get lucky method, and then there's the eliminate t method, and then there's the fiddle with one equation until you turn it into the other equation. So 3 different methods. I want to address a broad misunderstanding. This is a nice opportunity to address a broad misunderstanding. A lot of students think that, hey, I only need one method to do things. Why do I need 2? I can only use one at a time, so I'll just decide which one I like, and that's the one I'll use. Right? And that doesn't work in reality. In practice, rubber meets the road. It doesn't work because every method has its weaknesses. Every method applies only in certain circumstances, or it requires the user to do a certain process that in some cases is harder, in some cases is easier. Notice in the first method here, we had to get lucky. There had to be a sort of, I remember from trig class. You just have to get lucky and notice something. That won't always happen. You cannot rely on method 1. It's fantastic when it works. It's a good thing. can't assume it'll address every problem you'll face. Likewise, method 2 requires that you be able to solve for t. Can't assume that. Sometimes an expression has, what if the expression were a cubic polynomial of t? Can't solve for it, practically speaking. Right? So that method you can't always count on either. And this method here kind of assumes and requires that there be some reasonably convenient algebraic process for turning one expression into the other. In this case, yeah, sure, they're both kind of, what we loosely call linear functions of t, and so, yeah, it was pretty easy to do. That won't always be possible. Right? So what we have is, it's 3 different tools for the same kind of question, but different sorts of examples of the same kind of question. So what I want to strongly encourage you all to take an active sort of mental point of view on the following. Don't think of there being, okay, this is how you do them. Right? Think of the methods that I'm going to show you as individual tools that you will put in your little mental toolbox, and you pick the right tool for the right job. Right? And sometimes you need a Phillips head screwdriver, and sometimes you need a Torx screwdriver. They're both screwdrivers. You can't use the one for the other, right? You need the multiple tools. So always maintain a toolbox full of tools, and then pick the right tool for the right job. Okay. Alrighty. Next one. 3-dimensional. Right, we're in 3 dimensions. You can see they're in 3 dimensions. There's 3 coordinates. Right. All 3 of the above methods will kind of fail on this. So here's another tool for your toolbox. Sometimes you will find that you get lucky as follows. And even though the entire parameterization is unfamiliar, sometimes part of the parameterization will be familiar. We just got through seeing this one, right? Cosine t, sine t. Oh, yeah, that was example number 1, right? By the way, a really important one to make sure that you have right on the tip of your tongue. Parametrizing the unit circle, cosine t, sine t, comes up a lot. Okay, so now, can I just go around lopping off coordinates like that? Can I just ignore the t? Well, no, of course not. Right? I've got to think about what that means. If you have a point in space and you ignore that third coordinate, effectively what you're doing is you're looking at its shadow down in the xy plane. So the fact that I understand cosine t, sine t is basically telling me that the shadow in the xy plane is going around in a unit circle. It doesn't tell me what the curve is doing. It tells me what the shadow of the curve is doing. Everybody good? Okay. All right, now let's look at the other part. What would if I ignore x and y and look just at z? Well, that's pretty easy formula. Z equals t. What happens as time passes? Right? How does z behave as t increases? Well, z is t. So that just means z increases as t increases. And so while the x and y coordinates, the shadow in the xy plane is going around in a circle like this, right? Simultaneously, what you might call the shadow on the z-axis, the height is just going up, straight up in constant speed. So now what we can do is we can ask, okay, then how do I combine these together? I mean, after all together, I am interested in the combination. So I'm looking for a path. I'm looking for the movement of a point where the shadow in the xy plane is doing this, and then the height is rising at a constant rate. Right? Now, what curve does that? You got to use some 3-dimensional intuition. But I think that's a pretty easy pitch. that it makes a what we call a helix, kind of like a spring. Does everybody buy it? Yeah. Mm-hmm.
Should we take into account orientation for solving these problems?
That's a great question. So here the orientation is implied by how the parameterization is written down. So yeah, so you notice I put a little arrow on the end. So yeah, it is as written there. It is specifically going up. Sometimes we care, and sometimes we don't. So those specifics of when we're going to care and when we're not going to care is really, let me think about this. I think it's fair to say that's not going to come up until chapter 6. So for the moment, we don't need to care about that, but we eventually will care very much. Yeah. Great question. Anybody else? Yeah, okay. All right. Moving along. Okay, so in the previous examples, I gave you a parameterization, and the question was, what's that? We're going to turn it around backwards now. Instead of starting with a parameterization and trying to figure out what curve it is, we're going to start with a curve described some other way and try to figure out how to make the parameterization. And the process of creating a parameterization is called parametrizing. So how do we create parameterizations? Now, my own personal experience, subsequently my take on how to teach this course, is that knowing how to parameterize things is very valuable. I did a ton of parameterizing of stuff in my undergraduate days. And I'll mention, by the way, I know y'all are mostly engineers, right? And I'm a math guy, right? But I did do a second major in physics, and so I've been down a lot of the roads that y'all are going to go down in your engineering majors. A little different, of course. But anyway, in physics, you do a ton of parameterizing of stuff. So I like to get explicit about how to do that. Here's my favorite one. It's what I like to call the graph parameterization. It presumes that you start with a graph. We'll talk more about what a graph is a little bit later, but here let me just say a graph is a curve in the plane described by an equation where one variable is a function of the other variable. Right? So specifically, one of the variables is a function of the others. Not all equations have this property. But some don't, some of them do. And so, for example, if you have such a graph, here's the big trick. The way the graph parameterization works, just let t be your input variable. Whatever your input variable is, let t be that input variable. Stuff will just work out. Everything just magically fits. It's awesome, right? You just got to remember this one little trick. Whatever your input variable is, let t be that. So notice in this example down here, looking at this example, I have an input variable. Right here, y is a function of x. That means x is the input variable. Notice, per my own instruction here, I've let t be that input variable. And then I win because, there's just no way around it, because if x is t, then unavoidably y, being as it is x squared, has to be t squared. And we win. We have a parameterization. X and y functions of t. Position is a function of time. Totally awesome method, right? So make sure to be heads up on this. Make sure that you're proficient with applying this idea when you have a graph. Right? You use this trick. Let t be the input variable. Works every time. Okay. All right. Now, side note, quick observation. Sometimes it won't be written as a graph, but it still is a graph. This is actually a graph. It doesn't look, I don't have currently x equals or y equals, but you can do a little algebra and make that happen. Now you're going to have a natural urge, arbitrary, overemphasized convention in high school is that y has to be a function of x, but no, it doesn't. They're just letters. Alphabetical order has no mathematical significance, right? So you can solve for any variable in terms of any other variable, and it's still a graph. So in this case, I can't solve for y, but I can solve for x. No problem. X is a function of y, and again, following the rule, right? We identify what the input variable is. You let t be that input variable, and then that tells you what x has to be. And again, we win. Now I have position again as a function. Everybody happy? All right. Very good. All right. This is a fun example. Sometimes vector algebra is awesome. So y'all know vectors. Y'all know how to add vectors. Y'all know how to do linear combinations of vectors, stuff like that. So this is a great example how we're going to use that. It's going to take us a bit to see why it works so well. But the big point here is sometimes to take what you're interested in and view it as a sum of simpler vectors. Right? Now my scenario here is that I have a wheel sitting on the ground, and the wheel is rolling to the right. So it, as it rolls, it also moves to the right. And so, okay, here's my wheel, and it's rolling along to your right. Right? And then imagine that there is a reflector on the end of that wheel, as there often is on a bicycle, for example. Right? And what's going to be the motion of that reflector? Now, y'all have probably all seen the curve that I'm talking about. All you got to do is wait for kind of dark or dusk or something like that. The street lights are on, and somebody rides by on a bicycle, right? And there's that reflector, and it's typically near the end of the wheel, and that reflector will do this kind of jerky, kind of scallopy kind of path like that. That's what we're going to parameterize. By the way, if you try to do that by purely algebraic geometric methods, it's really, really hard. It's not technically impossible, but it's really, really hard, and you don't want to do that. So here's the much easier way to understand it. At any given moment, let's see here. At any given moment, let's say the reflector is there, as the wheel is where I have it drawn. I can talk about the position of the axle of the wheel, and I can talk about this. I'm going to call this the D vector, the sort of displacement vector where you start at the axle and then end at the reflector. Right? And previously discussed, that's D equals P minus A. And that tells me then that the point I'm looking for, where the reflector is just A plus D. So if I can understand that A vector, and if I can understand that D vector, add them up. That gives me my P that I'm trying to parameterize. Everybody good so far? I mean, there's much to follow. We've got to talk about how to figure out what those vectors are and where they are, etc. Okay. Cool. So A plus D. Okay, so let's take these one at a time. By the way, I am going to need to write them in terms of a parameter. T being a common choice, I got to decide what T is going to be. Very common choice in a case like this would be to let T be this angle. Part of my motivation here is that I can see already that some trig's going to come up. Right? We got a circle. Circle typically means trig is on its way, right? So get ready for the trig. When trig is going to show up, I think it's a good idea to let your parameter be an angle, because angles are what you do trig with. Okay? And I also like the fact that that angle has the intuitively satisfying feature that it starts. If you look here at the very beginning, when we start the wheel, it starts with that angle T being 0, and then as the wheel rolls, T increases. So it's a convenient choice. It's not the only choice. There are other choices you could make. It's perfectly fine. Go ahead, right? But I think this is going to be hard to beat in terms of convenience. So there's my parameter. And with that in mind, let's try to understand the location of the axle. Again, we have to take this one step at a time. So the axle. Good news, the axle just moves in a straight line, doesn't it? That's convenient. Much simpler to understand. I can see right away that the y coordinate is obviously just going to be a, whatever the radius of that wheel is. That's an easy part. The tricky part is to figure out what the x coordinate is going to be. And here's the clever observation. The x coordinate is that distance. Notice that distance is the amount of road that we've driven over so far. I'm going to say that differently. It's the amount of road that has touched rubber. And cool observation to make about how wheels roll is that the amount of road that has touched rubber has to equal to the amount of rubber that has touched road. Now, it's a physical appeal. If this weren't true, if blue weren't equal to green, the wheel would be slipping. Right? So presumably we're not slipping. Presumably this is a dry concrete kind of situation, dry concrete, good tread type situation, and there's no slippage, so rubber equals road. And what's awesome is that it's really easy for me to write down the formula for that rubber. Right? How much rubber has touched road? That's an arc of a circle of radius A, and that's pretty conveniently just the angle times the radius. High school geometry, right? Flashbacks to high school geometry. And so AT. Pretty clever, right? Okay. All right, now again, that only tells me about the axle, right? Where there remains this D vector. We've got to figure out how to understand the D vector. And the way I have it drawn, the D vector is sort of over here like that. But let me remind you, another key feature of vectors do not have locations. We draw vectors with arrows, and the arrow being something that, we're drawing it with a pencil or a pen, it's ink or graphite or whatever, right? That the arrow has to have a location, but the vector doesn't. A vector is nothing more than direction and magnitude, right? Doesn't say anything about location. So I can redraw that vector anywhere I want. I don't have to think of that purple vector as, as doing like this. That's hard to keep track of, right? The location doesn't matter. That vector, as the wheel rolls, is just doing this. It's just going around in a circle. If I just choose, for convenience, to view the tail as being fixed at the origin. In other words, if I'm thinking about the position vector. So that's what I want to understand. Now, again, in terms of that angle T that I have drawn in the picture here, and let me just zoom in for convenience, it's pretty immediate, very quickly, to write down this formula, right, in terms of that angle theta. That's our standard polar coordinate theta. Y'all remember the definition of sine and cosine, and you angle measured from the positive part of the x-axis, all that standard stuff. So there's your d in terms of theta, but that's not what I need. I need that d vector in terms of t. So I'm going to use the convenient observation that these angles, t and theta, always add up to 3 pi over 2. take that formula for theta, plug it into there, use the angle addition formulas that I memorized long ago and that I hope you all have memorized. And if you haven't, per the content syllabus, you do have to memorize the angle addition formulas. Plug into the angle addition formulas, and out comes, as needed, the d vector in terms of t. And so that finishes what we needed for this example. That let's see here. I got to get this all on the screen. There we go. So the big idea, was that axle, which we just solved for, plus d vector, which we just solved for, gives me the location of the reflector. Right, all I'm doing is just kind of plugging in to that established relationship, and bam, there's my parameterization. Position is a function of time for that reflector, doing, again, this kind of jerky, kind of scallopy kind of motion as the bicycle rolls down the street. And we're out of time, so it's a good place to end it. Okay, see y'all later. Have a good one, and see you on Thursday. Today's Thursday. See you on Tuesday. Have a good one.